let's try examples for higher order ODE, uh, the homogeneous solutions. Okay, so we will use our previous example, the spring mass and damper system. So example for the homogeneous solution of higher order ODE, which we use the example is the second order ODE. Okay, so that is our spring mass damping system. And we already derive our state space representation, which is the matrices representation, right? So d over dt, x1, x2 equals to 0, 1, negative k minus divided by m, negative c over m, x1, x2 plus 0, 1 over m, ft. Okay? So that is our spring mass damping system space representation. We will make the real numbers. So let's assume for m equals 1, k equals 2, c equals 3, ft equals to 10 to the 10e to the negative 2t. For those coefficients, of course, you can make the unit there, which is kilogram per second square, and that is kilogram per second. Forcing function is Newton, or kilo times meter divided by second square, something like that. Then we will also give the initial value. Since this is the initial value problem, the initial value is basically all passing to the same initial point. So by 0 equals to 0, y prime 0 will be equals to -5 for initial value problem. Okay. And what we can get is using the real number here, d over dt, x1, x2, that is equals to 0, 1. So -2 divided by 1, so it's -2. 3 divided by 1, -3. x1, x2 plus 0, 1, 10e to the -2t. So that is our system, spin mass damping system with the real number, real coefficient here. Then for the homogeneous system, which we will ignore the forcing function first, then later when we solve the particular solution, we will include the forcing function, okay? So for a homogeneous solution, what we have is d over dt, x1, x2 is equals to 0, 1, -2, -3, x1, x2, right? So you can write as x prime equals to ax, and in order to get this x function, you will solve the eigenvalue and the eigenvectors for system A. So what you can get is like your solution format x equals to some z function times e to the lambda t. Okay, so that is your solution size, since they are constant coefficient system. That's why your solution format is e to the lambda t, the exponential part. So x prime will be equals to lambda z e to the lambda t, right, based on this format. And it also equals to a times this x will be a z e to the lambda t. So az equals to lambda z, that is a standard eigenvalue eigenvector problem. And in order to solve the solution size z, then you need to solve the determinant of a minus lambda I times z equals to 0. So this is standard eigenvalue, eigenvalue, eigenvector problem. Okay. So what you need to solve this determinants of a minus lambda I equals to 0 and solve the root of these polynomials. Then you can get the final solutions. Okay. Let's try to use our system A. So the system A is 0, -2, 1, -3. Then A minus lambda I, that will be equals to negative lambda 3, -3 minus lambda. And the determinant of A minus lambda I will be equals to lambda times 3 plus lambda minus 2 plus 2. That is lambda squared plus 3 lambda plus 2 equals to 0. Then lambda 1 equals -2, lambda 2 equals -1. Okay, so that is our eigenvalue and eigenvalues. And based on the eigenvalues, you can get the eigenvectors. So when lambda 1 equals -2, then where you get this A minus lambda I will be equals to, okay, 2, 1 minus 2, that is -1. Okay, and you know this A minus lambda I j equals to 0. So your first eigenvalue and eigenvector will be 2, -2, 1, -1 times z1, z2 equals to 0. So the relationship between z1, z2 is z1 -z2 equals to 0. Then as long as these two values are equal to each other, then that can be your eigenvectors. So we can get oh, sorry, I do wrong. So here is 2z2 plus, so 2z1 plus z2 equals to 0. So as long as this z1 equals to -12, so z1 equals -12 of z2, that is fine. We can make an eigenvector, which z1 eigenvector is equals to, so let z1 equals to 1, then z2 is -2. Then you can also normalize it to be a unit of the eigenvectors, which is 1 over √5 minus 2 divided by √5. That is your first eigenvectors, and that is the normalized eigenvectors. Okay. Then when lambda equals to lambda 2 equals to -1, you have A minus lambda I. So this is lambda 2, that is lambda 1 equals to 1, 1, -2, -2. And in order to get the eigenvectors, A lambda 2I times z1, z2 will be equals to 0. So that 1, 1, -2, -2, z1, z2 is equals to 0. Okay, so you get the relationship of z1 and z2 where the z1 plus z2 is equals to 0. So the z2, which is the second eigenvectors when eigenvalue equals to -1, that is 1, -1. And you can also normalize it, which is 1 over √2 minus 1 over √2. Okay, so that is your eigenvalues and the eigenvectors when you have this distinguished root. Then after that, we will construct our final